So hello everyone, this is lecture 3 for the thermal physics. In the last lecture we discussed some degree of freedoms and how we can calculate the specific heat or the energy of any gaseous system in monatomic, diatomic or anything just by the degree of freedoms, and what possibilities we have for the degree of freedoms. We all talked about that. Okay, so let's see some questions regarding that. If there was these questions actually asked in the previous years. Okay, so if a gas is there and transitional degree of freedom is given 3 and rotational 3, then you can find the CP or CV, CPM or CV. How? Means total degree of freedom will be 336, then 6 into 1 by 2 kT, that will give 3 kT, U equal to 3 RT, CV and CP. Then CP upon CV will be this. Okay, CP, how you find CP? That is from the Mayer's relation, CP minus CV equal to R. Okay, so I didn't write the whole question, just I took the points which you will see and how you can solve. Okay, so there was one more question, like it is not given that it is CP or CV, but the C is given 5 by 2 R. Then you have to select the options, means what kind of gas it is, the possibility of this gases for which C is equal to 5 by 2 R. It can be monatomic, rigid diatomic, non-rigid diatomic, or can be monatomic and or rigid diatomic. Okay, so if it will be monoatomic, then U is for the monoatomic 3 by 2 RT, then it will give you CV equal to 3 upon 2 R and CP 5 by 2 R. So we are getting somewhere 5 by 2 R for monoatomic. Let's check for the second one, rigid diatomic. What is the meaning of rigid? Means you are not having any vibrational mode. So transition 3, rotational 2, total 5, and CV will be 5 by 2 R, CP 7 by 2 R. So here also you are getting this term 5 by 2 R, just like that. Let's check for the third one, non-rigid diatomic. If there is no rigidness, then vibration mode will be counted. So transition 3, rotation 2, vibration 2, that will give you 4, 5, 6, 4, 6, 7 by 2 R, and CP will be 9 by 2 R. So here we are not getting this term. So our fourth option is can be monatomic and rigid diatomic. So it can be monatomic or rigid diatomic. So both possibilities are there. Monatomic 5 by 2 R we are getting, or the rigid diatomic we are getting 5 by 2 R. So these both can be, and it is given in the D option that it can be monatomic or rigid diatomic. So D option is correct. Now there was one more question in which it was written that only 1 by 1 vibrational mode is excited. So from there we taken out this, that FV is equal to, means one mode is contribute to the 2 degree of freedoms for the vibration. So FV will be 2, FT3, FR3. So total it was a 3D polyatomic gas it was given. So that's why we taken transition 3 and rotational also 3, because it is 3D polyatomic. Total degree of freedom will be 336, 8, and we need to find the CV. So it will be 8 by 2 RT and CV will be 4 R. Okay. So there are one more question, you need to find the CP, and it is given that it is something like this and it is rigid. So FV will be 0, so FT equal to 3, FR equal to 3, because this type of have will 3 rotation degree of freedom. So 6 will give you 6 by 2 RT, it will give you 3 R as CV. CP will be CP minus CV equal to R, that will CP equal to 4 R. So you will get the answer. There was one more question in which Hamiltonian was given. You didn't study this yet. I will teach you this in the classical mechanics. Okay. So just here remember this, that Hamiltonian represent the total energy. Okay. So in the energy term we are having this and this. So square terms gives us the degree of freedom. I already told you. We need to find the square terms. So here is one square term is here. So it will contribute to the half kT. And if you are getting something like this, means x to the power n, which is not 2. Okay, so you will use this formula, equal to alpha x n, then average energy will be kT by n, so here it is 4, so it will be kT by 4. So E1 E2 you get, total energy you can find, then just same differentiate with respect to temperature, you will get the CV and CP. Okay, so it is simple, just remember this, only the much I told you. Further we will study in classical mechanics. Now let's start for the today's session, that is for the mixture of gases, and we need to find some thermodynamic parameters for those mixture. So how we can, so just remember, if we are calculating the change in internal energy of a gas when T changes in the thermodynamics, we always use this formula. that will be NCV dt, means we don't consider CP and all. Delta U will be given by this formula, whether it is isochoric or isobaric or adiabatic. Okay, so this will be given by this formula only, just remember this. And where N is number of moles of a gas, CV is molar specific heat, fixed volume, and dt is nothing but change in temperature. This is T final minus T initial. So remember this formula for the change in internal energy. And Cp minus Cv equal to R, this is called the Mayer's relation. For 1 mole we can write this formula. So just divide by Cv here, Cp upon Cv minus 1 R by Cv. It is gamma. So we can write specific heat, molar specific heat in terms of gamma also. So it will be gamma minus 1 will came out in the denominator, Cv will be here, Cv equal to R upon gamma minus 1. So we can write Cv in form of this also, and by this formula we can calculate Cp will be gamma R by gamma minus 1. So just remember these formula also, we can use them very efficiently in the questions. Okay, so just remember them. Now thermodynamic parameters for a mixture of gases. Okay, we need to find the parameters for a mixture of gases. So what parameters they can be? The equivalent molar mass. You studied what is molar mass, that is for the mass means if you consider it in gram, then that will be for the 1 mole of that gas. Okay, means if it is given that molar mass is 40, then 1 mole of that gas will have weight 40 gram. Okay, so if there is a mixture of gas, then you need to find the equivalent molar mass. How can you find? When N1 moles of a gas with molar mass M1 are mixed with N2 mole of gas with molar mass M2, the equivalent molar mass of the mixture will be given by this. M will be N1 M1 plus N2 M2 N1 plus M2. Here M1 is molar mass of first gas, M2 is second gas, and this. For N numbers you can just add up. Okay, now if you need to find the internal energy of a mixture and specific heat of the mixture, so internal energy will be given by just sum of the internal energy of two gases. Okay, final energy will be sum of individual energies, and from here du can be written as du1 plus du2. Now du is given by NCV dt, I already told you, that is for the final mixture, and this is for the one gas N1 C1 CV1 dt, this is for the second gas N2 CV2 dt. Now from here you can find the Cv, that is specific heat for the final mixture, that will be given by this divided by this. Okay, so you can write this will be the specific heat. So we find the specific heat, we find the internal energy of the mixture, and these are for the all type of gases. I am not talking here about the ideal gas. Okay, this will be applicable for all gases. Now Cp of a mixture you need to find, then Cp will be Cv plus R, just use this plus R, you will get this type of formula, and when you rearrange you will get Cv1 plus R, Cv2 plus R. Here it is Cp1 Cp2, so you will get the same formula just like this, N1 Cp1 plus N2 Cp2 divided by N1 plus M2, like here. So it will be easy to remember. Now if you need to find the adiabatic coefficient for the mixture, or sorry, adiabatic index, gamma for mixture we have N1 plus N2 Cv equal to this formula. From here we know Cv we calculate in terms of gamma, that was R upon gamma minus 1. So just write it here, N plus M2 R upon gamma minus 1. For first gas it will be N1 R upon gamma minus 1. For second one it will be N2 R upon gamma 2 minus 1. Now from here R will be cancelled out and we'll get this formula. Now if you know the values of gamma 1 and gamma 2 for the individual gases and their number of moles, you can find the gamma, okay, for the mixture. So it will be easy. Now if we are mixing two different gases, and different gases, actually what I mean actually that they can be monoatomic or diatomic, monoatomic or triatomic, polyatomic, diatomic, triatomic, diatomic. Okay, means all gases which are monoatomic like helium, argon, they will be same gases. We consider them same because we don't differentiate them on the type of their nature. Okay, if they are monoatomic, they are same gas. If they are all diatomic, they will be same gas. But one is monoatomic, second one is diatomic, then they will be different. So mixing of two different gases. Example, monoatomic and diatomic. So this will be for T1. This is temperature for first gas. This is temperature for second gas. This is CVT, that is for the mixture. Now U1 internal energy for the first system will be given by N1 CV1 T1, for second mixture N2 CV2 D2 T2, and for the final mixture N1 plus N2 CVT. Here N1 plus N2 we write N. Okay. Now from the internal energy formula we know that final energy will be sum of individual energy. So write it like this. From here we can find the final temperature, that will be N1 CV1 T1 plus N2 CV2 T2, N1 plus N2 CV. Now we still don't know this CV, and we calculated this CV for the final mixture from here. CV, this was this. So use this formula. CV is this. Substitute this in here. Then N1 plus N2 will be cancelled out, and we'll get the final formula will be this for temperature. N1 CV1 T1 plus N2 CV2 T2, N1 CV1 plus N2 CV2. This is final temperature for the mixture. Now that was for the any gas, real gas. Now mixing of identical ideal gases. If we are mixing the ideal gases, then what happens for this temperature and all? Okay, and they are identical, so they will have the same specific heat capacity, that is CV. So for first, U1 will be N1 CVT1, U2 N2 CVT2. Final will be N1 plus M2 CVT. So final energy will be sum of individual energy. So just write it like this. From here CV will be cancelled out from all factors. T will be given by N1 T1 plus N2 T2, N1 plus N2. Okay. So from here you can find, and you can also make it like for the ideal gases we know this formula, N1 equal to PV upon R RT, PV equal to nRT, you know the formula from here, N equal to PV upon RT1. So just substitute it here for N1. T1 will cancel out, T2 will cancel out, and R will be cancelled out from all the four factors, and you will get this type of formula. Final temperature will be P1 V1, P2 V2, P1 V1 upon T1 plus P2 V2 upon T2. This is the final temperature for the ideal gas. Okay, for the ideal gas only, which are same gases in the final mixture. So identical gases, what we mean actually by the identical gases, that is either monoatomic, helium or argon, or diatomic, that is N2 O2 H2 etc. Okay, so we call them the identical gases. Okay, I already told about you about this thing. Okay, so it is not that much complex. The monoatomic means they should have the same number of atoms, then they will have the same specific heat. Okay, CV will be same. We already discussed about in the last lecture that how all the monoatomic gases have the same, and diatomic same, and triatomic same, and polyatomic same. Okay, so we differentiate them on the basis of their number of molecules or number of atoms, but not on the nature. Okay, they are independent of their nature, their specific heat. Now there were some questions actually asked in the previous years. So they were just based on this formula, means final temperature was asked for the ideal gas, so you were using this formula, and this expression is also asked in the question, is what can be the final temperature if you know the P1 V1 T1. Okay, so let's end the today's session here. Just revise this what I told you. If you didn't getting anything, then just watch the previous lecture, you will get the idea. Okay, so thank you.